A very good morning. Today I am going to discuss the probability control limits. And I am going to take few examples on the P chart or C chart or NP chart like that. So let me start with some particular example so that I can be very fast. Take down this particular problem. A company manufacturing laminated spring wishes to use suitable control chart to maintain the quality of its product when produced by a new alternative process. The number of minor defects detected on the first 50 springs produced were as follows. So here he has given number of defects and number of springs. Zero, 1, 2, 3, 5, 6 and 4. 6 and 4. 10, 28, 3, 10, 28, 3, 3, 1, 5. Okay. So totally how many springs are there? Totally the total number of springs inspected are 50. Okay. And how many defects have been found out? 1 plus 2, 21. So out of 50 springs, total springs inspected were 50. Out of 50, 21 defectives were found. Defects, not defectives, 21 defects were found out. This is the thing. He says, use this data to set up an appropriate control chart. Okay? We have to set up the appropriate control chart. The first thing, that is what I told you, which control chart is to be used. Okay? He has already collected the data. But before collection of the data, our job is, a decision maker job is, which control chart is to be used. That if we had thought in the beginning itself, then it becomes much more easier for him. So, however, it is a sort of simulation. Now the facts are given and we have to work back in the reverse way. Because when we try to implement it, it is different. Now, planning, that is top-down approach, and the implementation bottom-up approach. Now already the planning, everything is done. Now we are going to implement, or we are going to find out that one. Already it has been implemented and these values have been collected. Now, which he is asking, use this data to set up an appropriate control chart. Which control chart is to be used? Here, these are not the miserable data. These are the counts. number of things. That is what he has given. Is whether if they were number of defectives, then we would have used either P chart or NP chart. But he says it is number of defects. Number of defects means we will be narrowed down to either C chart or U chart. Number of defects. We are going to use C chart if the sample size remains fixed from one sample to the another sample. These are the different samples. For example, there are now 1, 2, 3, 4, 5, 6, there are 7 samples collected. And first sample has a sample size of 10, second sample had a sample size of 20, third 8, like that. And the sixth one only 1. Okay, that means sample size over the period, it was differing. Hence we cannot use C chart. We have to use the appropriate control chart for this purpose is U chart. Okay, that is what appropriate, that because this will carry more weightage. The control chart that is to be used is U chart. U chart is to be used. Okay, that decision is taken. Okay, why? I explained you. Again, if you want to recapitulate, since the sample size is varying, first one is the number of defects are given. That is why U or C chart is to be used. And since the sample size is varying, we have to use U chart. Okay, that is what it means. Now, what is the upper control limit for U chart? Upper control limit for U chart is U bar plus 3 under root U bar by N. Central line U bar and lower control limit U bar minus 3 under root U bar by N. Okay, because this is per unit, that is what you need to find. On an average, what you have to find out? On an average, how many defects will be there per spring? Okay, how do we calculate? The total number of defects of the total sample, total numbers inspected, which are 50. Out of 50 samples collected springs, 21 defects are there. Because that is what always we talk about, the average value. Okay, but here you can see for some 10 springs there are no defects at all. And if you look at this one, when the sample size is 1 only, for one spring it has got 6 defects. This is either we can say pitfall or what, I don't know, or the beauty of this statistics. That is why it calls for lot of inferences. Only the experts can be able to answer these things. Otherwise, it is most likely it will be misinterpreted. That is what we need to understand. Okay. Now at this thing, that is what we are saying. So one sample only it will have 6 defects. Here, out of 3 springs, there are 5 defects and other things. Then most likely this may not belong to this particular distribution, or on that, at that time the process was out of control. That is what at the outset it appears. But we need to prove it statistically. Okay? Just at the outset, I can say that by intuition, that is what we are saying. I may be right or I may not be right. But I need to, if I have to think in a rational way, I need to prove it mathematically or statistically. That is why, hence, I am fixing this upper control limit, lower control limit, like that. Okay? In any case, I have to find out the U value. U value for this one is how much? 0. That means actual U value I am finding out. That means defect per unit. Defect per unit, I denote it by DN. dn I denote it as defects per unit, per spring in this case. That means 0 by 10, it is 0. 1 by 20, 2 by 8 is 0.25, 3 by 3 is 1. Okay. So if we go on calculating like that, so we'll get these values. Point not 5, this is 0.25, 3 by 3 it is 1, then this is 5 by 3, 1.66, this is 6 by 1, 6, this is 4 by 5, 0.8. Okay. Now average value, how do we find out the average value? There are two ways of finding out this average value of U. Either you can find out by this one, 21 by 50, or you add up all these things and divide it by 7. Let us see. Both the things will work out for your satisfaction. So now, if I add up these things, it is going to be now this is 9.76 divided by okay. Now we'll stop at this one. That means dn value we have calculated, and next we have to find out what is the average value, because out of 50 springs it has got 21 defects. So 21 divided by 50, this is equal to 0.42. U bar expected out of these things would have been 0.42. So U bar value is, that means total number of defects divided by total numbers inspected. So this is what it gives. U bar, this is equal to 21 by 50, this is equal to 0.42. And individual dn values we have found out like this. Now since the sample size varies, the upper control limit and the lower control limit, they are going to vary, because upper control limit also it has got a value n over here, and lower control limit also it is n. Hence, individually I need to set up for these things. So here I will write UCLU. This is equal to U bar plus, we are going to use 3 sigma limits, U bar by n. In general, that is what I have written. So this value I am going to put what here, LCLU, U bar minus 3 under square root U bar by n. Okay. So now let us calculate first u bar by n, that is for first one, u bar is 0.42 divided by n is 10. This is 0.042, its square root 0.20 multiplied by 3 sigma, that is 0.6148 plus 0.42, that is 0.6148. This we will remember that one, 0.6148 plus 0.42. This is 1.03. This is upper control limit is 1.03, and this is 0.42 minus 0.61. This is going to be negative, hence it is considered as 0. Then we will take up the second one. U bar is 0.42 divided by, sample is 20. The square root is 0.144 multiplied by 3. This is equal to 0.43. 0.43 plus 0.43, this value it works out, 0.43 plus 0.42, 0.854. Where this will work out to be negative, so hence it is 0. And the third one we are going to consider, that is u bar is how much? 0.42 divided by 8. This is equal to 0.05. Square root of this one is 0.22 multiplied by 3. This works out to be 0.68. 0.68 plus 0.42. This works out to be 1.107. 1.107. And here, since the 3 sigma, this one is greater, so it works out to be 0. Next one, it is 0.42 divided by 3, 0.14, square root 0.374 multiplied by 3. This works out to be 1.12 plus 0.42. This is 1.54. And this is negative, hence it is to be 0. Similarly, for this one, it is 0.42 divided by 3, and its square root 0.374 multiplied by 3. This is 1.12 plus 0.42, 1.54, and again this is 0. Okay. Now if I look at this, .42 divided by, that is square root I am going to take, 0.64 multiplied by 3, 1.94 plus 0.42, this is 2.36, and this is obviously to 0. And the last one, 0.42 divided by 5, its square root 0.28 multiplied by 3, this equals to 0.86 plus 0.42, 1.289, and this is 0. You got this one? You try to observe these things. Now upper control limit here is 1.03, 0.854, 1.107, 1.54, 1.54, and 2.36, 1.89. and lower control limit, they are 0. If we say that this is the actual value we are going to compare, it should lie between these two limits. First one, yes, it lies between this limit, right. This one 0.854 we expected, but we have got actual 0.05. This is also correct. 1.107, this is the thing. 1.54 expected, actual 1. Expected 1.54. Try to understand here. Expected 1.54, but we have got 1.66 actual. So this is out of control on this day. And this one expected 2.36, but actual, how much we have got? 6. This is also out of control. This is the thing. 1.289 expected, 0.8. So what always we compare is with the actual value with respect to the expected value. Expected values are calculated using the facts or statistical things. That is all, in all the statistics, we are going to use these things only. Okay? That means we are going to compare the actual things with the expected value. In statistics, that is what. Okay? Now, these 2 points, that is the 5th and the 6th sample, they are out of control. Okay? Now, if these things are to be revised, how you will do? These are the trial control limits I have fixed earlier. They will go on varying. Now, if I want to fix, and the process is statistically not controlled, that is what we can say. Why? 2 points they have fallen outside the control limits. Now, next what we need to do, you revise this thing, you eliminate these 2 points, and then again calculate the values. And then again test with the remaining 5 values. So, if all of them, they fall within the control limits, then use those things as use those U bar value for other calculation purposes. That is the trick over here. Is it understood? This is how it works. Similarly, this U chart is similar to P chart. In P chart also, when the sample size it varies, these things will go on varying. Upper and lower control limits are going to vary. They will not remain fixed. Only in NP chart and C chart of control charts for attributes, all the 3 things are fixed. That means they are straight lines. Upper control limit, lower control limit, as well as the central line for NP chart and C chart. They will be horizontal lines, straight lines. Whereas in case of P chart and U chart, it may or may not be a straight line, upper control limit and lower control limit. But central line is a straight line. So this is the gist you need to understand. Now one more problem I will take up, because one more thing I want to drive at, and then we'll talk about the probability control limits. If the time permits, we'll discuss about those probability control limits today, or tomorrow class will be maybe the last concluding class for control charts for attributes, or we can sum up both the units, that is control charts for variables as well as the control charts for attributes. Okay. So let me take up one example, a typical example, because I want to drive at certain points. I will just read the problem. So I am not going to fully solve it, but only part of it. In a factory producing spark plug, the number of defectives found in inspection of 20 lots of 100 each is given below. So he has given the lot number and the number of defectives. Okay. So there are 20 lots like this. The number of defectives, they are varying. They are varying from 3 to as large as 12. They are varying from 3 defectives to 12 defectives. And mind it, its lot size is fixed. Lot size is fixed and it is 100. Likewise, there are 20 lots. Each will contain 100 samples. He says, construct the appropriate control chart and state whether the process is in statistical control. Okay. Which chart we are going to use here? Since the number of defectives are given, then either you can use P chart or NP chart. Okay. No harm. But since the sample size is fixed, that is 100. Every time we are taking the sample size as 100. So the NP chart is the appropriate control chart. But however, P bar is to be found out. Whether it is P chart or NP chart, P bar is to be found out. Okay, here P bar works out to be, because the total number for all the 20 lots, if I consider that one, it works out to be total number of defectives are going to be total number of defectives. If I add up all those things for those all 20 lots, that is 123, and total numbers, those things have been inspected, 20 lots, and each lot will be consisting of 100 items. The total numbers inspected, this is equal to, that means divided by this. This is what I say. So this works out to be 0.06. Okay, this works out to be 0.06. So P bar is equal to 0.06. Okay, so whether you use NP chart or P chart, this is going to remain same. And if we consider this one, and upper and lower control limits we can find out for P chart or NP chart. If we use P chart, then it is value is also this N, it is fixed every time 100. So upper control limit, it works out to be 0.13, and the lower control limit, it works out to be 0. Central line is 0.06. Okay. And if you are going to use NP chart, it is very simple. The upper control limit, it is going to be 13, and lower control limit is going to be 0. Because just multiplying this one by 100, you are going to get it that way. And the central line for NP chart is going to be 6. The average number of defectives we can expect with that one is 6. So all the points, because it varies from 3 to 12 defectives, hence all the points, they fall within the control limits. This is the answer for this. Okay, I have just read out and I have put certain figures over here. But what is that is interest of for us is the next thing, B part. Determine the sample size. Determine the sample size when the quality limit not worse than 9% is desirable. Not worse than 9% is desirable. That means up to, I can go fraction defective of how much? 0.9%. See, determine the sample size when a quality limit not worse than 9% is desirable. And bad product will not be permitted more than 3 times in 1,000. What does it mean? This is what you need to think. Okay. One is, he says quality limit not worse than 9%. That means upper control limit. We can think now. What we can think about is upper control limit. If we are going to use P chart, that means upper control limit of P chart is equal to how much? P bar plus 3 under root P bar Q bar divided by N. This is equal to 0.09. Okay. Now what is going to happen now? P bar is fixed. P bar is 0.06. Hence Q bar is 0.94. Okay. What he is asking you, just see. Determine the sample size when the quality limit not worse than 9% is desirable and the product will not be permitted more than 3 times in 1,000. More than 3 times in 1,000, it works out to be how much? 3 sigma limit. That is what we have been telling. Okay. It is 0.3%. Okay. 0.3. More than, it is not, it is this permitted in the sense that is what it says. 1,000 will not be permitted more than 3 times in 1,000. That means it is out of 1,000 product, only 3 defectives can be permitted. So it works out to be 3 sigma limit. Okay. That means 3 we are going to use. That means this is the 3. That is how I am going to fix this one. He has said 3 defectives per 1,000. If he had said not 3, 5 defectives, then instead of per 1,000, then it would have been changed. Try to understand. These are the things. Okay. So now, which is unknown here? This is 0.09. P bar is known. P bar, that means we want P bar plus 3 under root P bar Q bar divided by N is equal to 0.09. He wants us to find out N. P bar is known as 0.06 plus 3 under root P bar, that is 0.06 into 0.94 divided by N. This is equal to 0.09. So only unknown is N, and if we solve this one, then N works out to be 564. Okay? Because if we want to keep it down to that level, there is no other way but to increase the sample size. Here the sample size is 100, with the result the maximum upper limit we have fixed it as 0.1311, maximum permitted, because if I can reduce it, if I go on increasing this N value, that is what it says, because it is in the denominator, hence our accuracy, this thing and other things, it will go on increasing. If I want lesser number, because with the more the number of the samples, lesser will be the upper limit, hence more accurate results can be got. This is what it tells us. So I have talked briefly about the control charts for the fraction defective, and I have solved the problem on control chart for the defect per unit, and certain insight about the probability control charts are given. So tomorrow I will take up some probability control limits, and I am going to wind up the discussion on the control charts That is both control charts for attributes as well as variables. Okay, thank you.